Jupiter floats in the darkness like a colossal beacon. From afar, it looks like a striped sphere, a gas giant so massive that it outweighs all the other planets in our system combined. What kinds of forces create those alternating shades of orange and white? Today's journey is not just about a planet, but a dynamic laboratory where atmospheric physics and planetary evolution converge. This giant, composed mostly of hydrogen and helium, the very ingredients stars are made of, never ignited into a star. Instead, it radiates an internal glow, a quiet testimony to its turbulent origins. What drives this internal heat? How do the powerful winds carved across its surface maintain the continuous motion we observe? Today, we'll take a closer look at its faint halo of rings and distant moons lost in the glare of the giant. What stirs in the depths of this planet? Where have the obvious surface elements gone? What illogical phenomena are hidden at its poles? Our journey, accompanied by original imagery from NASA probes and enriched with meticulous animation, invites exploration of these mysteries. Up close, Jupiter's face breaks into bright bands of clouds, ochre brown belts, and pearly white zones running parallel to its equator. These atmospheric stripes are not static markings, but visible manifestations of powerful jet streams racing around the planet at immense speeds. Jupiter's atmosphere is organized into east-west flows that alternate as they encircle the globe, intensifying multiple times from the equator to the poles. In the lighter zones, clouds of ammonia ice rise from below, reflecting sunlight in white and pale gold. In the darker belts, we see deeper layers of the atmosphere, where clouds tinted by compounds like ammonium hydrosulfide give off rusty and amber hues. Each adjacent band moves in the opposite direction of its neighbor, a giant planetary pattern etched by ferocious winds. The speed of these jet streams can reach hundreds of miles per hour, far exceeding any hurricane on Earth. Some winds in Jupiter's upper cloud layers exceed 400 miles per hour, and at certain altitudes even more. The Coriolis effect on this rapidly spinning sphere fractures the atmosphere into dozens of east and west moving jets, between which lie the bright zones and dark belts. The planet's atmosphere is divided into zonal flows, essentially a system of cyclonic and anticyclonic jet streams. Deep below, Jupiter's internal heat, left over from its formation, drives convection that continuously fuels these flows, sustaining eternal winds. The jet streams form sharply defined bands that remain astonishingly stable over time, yet their boundaries are turbulent and chaotic. We observe fine waves and curls where fast winds whip past each other, a sign of intense wind shear shaping the cloud tops. Ammonia and water vapor rising upward condense into bands of high white clouds, while in other areas, descending air clears the sky to reveal the dark layers beneath. The result is a marbled pattern encircling the entire planet. Amid Jupiter's bands, there is a storm raging like no other, the Great Red Spot. This salmon-colored oval cyclone has been raging in the planet's southern hemisphere for centuries, and it's large enough to engulf Earth entirely. More precisely, the Great Red Spot is an anticyclone, a high-pressure vortex spinning counterclockwise, opposite to a typical cyclone, and towering above the surrounding cloudscape. In this close-up, the spot's clouds swirl into a dense oval ring the color of a faded brick. A high-altitude haze gives the spot its reddish tint, though its exact chemical makeup remains somewhat mysterious. It may be colored by complex organic molecules or phosphorus-bearing compounds dredged up from the depths. Inside, bands and swirls spiral like a giant eye. Around its edge, winds rage at speeds of up to 268 miles per hour, sculpting cloud matter into a form that has fascinated astronomers since it was first observed over 150 years ago. White ammonia clouds swirl around the spot's perimeter, stretching and being pulled into the vortex. From time to time, smaller storms collide with the Great Red Spot, either bouncing off or being absorbed. It acts as a ruler of Jupiter's atmosphere, influencing weather far beyond its immediate borders. In recent decades, observers have noted that the spot is gradually shrinking and changing shape. It was once twice its current size. Nevertheless, it remains the largest storm in the solar system. The Great Red Spot completes a rotation roughly once every 6 Earth days. At its center lies a relatively calm area compared to the fierce surrounding jets. High above the storm hovers a dome of reddish haze, setting it apart from the brighter zones nearby. Within this giant, lightning has occasionally been observed, briefly illuminating the clouds from within. Far beneath the cloud tops, the storm likely extends for many miles. Though instruments aboard the Juno spacecraft suggest it may be relatively shallow compared to the planet's radius. Still, it stands significantly taller than the surrounding cloud layers. The Great Red Spot is essentially a massive, long-lived, high-pressure system, something akin to a hurricane's inverse, with winds spiraling at its top. It's persisted so long that it may have even changed form over time, merging with several major storms from centuries past. Beyond the Great Red Spot, Jupiter's entire atmosphere is filled with smaller storms and vortices. The planet is a canvas of ever-changing turbulence. Along the belts, we find elongated white ovals, small anticyclones similar in nature to the Great Red Spot, but much smaller in size. Some last for decades, while others form and dissipate within a few weeks. At one latitude, a chain of such storms curved around the planet's southern hemisphere like a string of pearls. These white ovals can merge over time. In 2000, 3 small ovals combined into a larger storm called Oval BA. Oval BA, nicknamed Red Spot Jr., later turned red and reached a size roughly half that of the Great Red Spot. Between the major spots, Jupiter's clouds are full of turbulent flows. At the boundaries of the fast jet streams, the wind shear creates twisting filament-like patterns. We observe swirls where dark belts meet light zones, and likely these are Kelvin-Helmholtz waves, formed when 2 air layers slide past each other, creating a wave-like cloud. In some regions within the belts, small, dark barges drift by, while bright pop-up clouds resembling popcorn mark powerful convective thunderstorms rising upward. Jupiter's atmosphere has no solid surface to interrupt the winds. Storms can dive deep and last longer than any earthly equivalent. Following the curve of the planet, we see countless small rotating structures, from compact vortices just a few hundred miles across to vast chaotic regions where multiple vortices interact. These collisions and mergers regularly disrupt the rest of the stripe pattern. For example, a turbulent region often trails behind the Great Red Spot, where the spot's flow disrupts the neighboring belt and creates clumps of vortices and pale clouds. This turbulence acts as a storm nursery. New vortices can be born in these chaotic shears. Yet amid this apparent chaos, there is a kind of order. Each storm tends to stay within its latitude band, held in place by powerful zonal jet streams. Despite the striped and chaotic look of Jupiter's equatorial and mid-latitude regions, surprising order emerges at the poles. Flying over the poles, Juno discovered polar cyclones arranged in geometric symmetry. At Jupiter's north pole, 8 massive cyclones are evenly distributed around a central one, forming a near-perfect octagon of storms. Each of these polar cyclones is enormous, about 1,500 to 1,800 miles across, but they sit tightly next to each other without merging. All spin counterclockwise, their spiral arms nearly touching, yet balance is maintained, as if something repels them from each other, so no one crowds too closely. The pattern is truly striking, a polygon of synchronized cyclones. Bizarre, yet stable. The South Pole displays a similar scene. It originally had 5 cyclones surrounding a central one, and was later joined by a 6th, forming a hexagon. These polar clusters have remained stable for years of observation, barely shifting. The symmetry suggests hidden physics, perhaps a fine balance of vortex flows and jet stream boundaries locking the storms into place. Suddenly, a bright flash lights up the planet's clouds. There's lightning on Jupiter. For a moment, the tops of the clouds just glow intensely. Then darkness returns. Jupiter's thunderstorms produce lightning that rivals and even surpasses that of Earth. Since Voyager first spotted them in 1979 as fleeting flashes atop the clouds, we've known that lightning on Jupiter occurs deep in the layers of water clouds where temperatures and conditions are similar to Earth's storms. But NASA's Juno mission found a new twist. The planet also has shallow lightning. That's electrical discharges high in the atmosphere within clouds made not just of water, but of an ammonia-water mixture. In these cold upper layers, where temperatures drop to about negative 126 degrees Fahrenheit, normal liquid water can't exist. But Jupiter's abundant ammonia acts as antifreeze. During powerful storms, icy hailstones are hurled upward some 15 miles above the usual cloud decks into regions rich in gaseous ammonia. Ammonia melts the ice, forming droplets of ammonia water slush. In this strange alien thundercloud, collisions between rising ice crystals and falling hailstones saturated with ammonia, which earned the nickname mushballs, generate static electricity. The result? Lightning crackling through Jupiter's upper atmosphere, far higher than we thought lightning could form. These shallow lightning bolts flash through ammonia clouds, briefly illuminating towering storm structures with eerie blue and gold light. Juno detected these flashes on the planet's night side, each lasting just milliseconds, yet glowing nearly as brightly as Earth's familiar lightning strikes. Deeper down in more conventional thunderstorm regions 30 to 40 miles below the cloud tops, lightning strikes are just as fierce. Here, water exists in all 3 phases: ice, liquid, vapor, just like in Earth's cumulonimbus clouds, promoting energetic charge separation. Some lightning bolts are colossal, releasing several orders of magnitude more energy than typical lightning on Earth. Juno detected thousands of lightning flashes. Hearing their radio crackle so-called whistlers as it flew over the cloud tops. Interestingly, it was Juno's discovery of shallow lightning that solved the mystery of why ammonia seemed to be missing from Jupiter's air. Mushball hailstones were carrying the ammonia deep down, removing it from the upper atmosphere. Once more, we witness a flash piercing a distant cloud bank. Lightning illuminates billowing cloud towers rising above the surrounding haze. These convective towers can reach heights of 30 miles, driven by the planet's internal heat. In the brief glow, we glimpse the outline of a colossal thunderhead, possibly the source of ammonia-rich hail falling downward after the strike. Now let's go beyond the clouds and storms. High above the poles of Jupiter, There are shimmering auroras of staggering power dancing in the sky. Each pole is surrounded by the constant halo of glowing auroral radiation, crowning the planet's darkness with an otherworldly blue-violet light. Jupiter's auroras are the most intense in the solar system, hundreds of times more energetic than Earth's northern lights. Unlike the fleeting auroras on Earth that appear only during solar storms, here, the auroras never cease. They're driven not only by the solar wind, but also by the planet's immense magnetic environment. Jupiter has a magnetic field estimated to be between 16 and 54 times stronger than Earth's, generated by metallic hydrogen rotating deep within the planet. This magnetic field captures charged particles and channels them toward the poles. When these high-energy particles collide with Jupiter's upper atmosphere, they excite hydrogen molecules, causing them to fluoresce in ultraviolet and infrared light. The result? Gigantic oval rings of auroral light encircling each pole. In the image, the northern aurora glows with an electric blue light spiraling under the influence of magnetic forces. The auroras are partly powered by the rotation of the planet and its moons. Volcanoes on Io, Jupiter's innermost major moon, spew tons of ionized sulfur and oxygen, which get trapped in Jupiter's magnetic field. As Jupiter rotates, taking less than 10 hours, it drags the magnetosphere with it, flinging ions toward the poles. Io's contribution is so significant it creates footprints in the aurora, bright spots corresponding to magnetic connection points between Io and the planet's atmosphere. Similar footprints come from Europa and Ganymede. One of these can be seen as an especially bright, pulsating auroral spot at the edge of the northern oval. In addition, bursts of solar particles, the solar wind, can intensify the glow, causing it to flare even brighter and more dramatically. Observations from Hubble have shown auroral curtains reaching thousands of miles above the cloud tops, far surpassing anything we've ever seen on Earth. However, even an observer standing within Jupiter's atmosphere would not be able to see these massive glowing rings overhead. That's because they glow in wavelengths that our eyes can't perceive, primarily ultraviolet. On top of that, they also emit X-rays. Essentially, Jupiter's auroras shimmer, emitting high-energy X-rays, a phenomenon still being studied to determine how these particles are being accelerated. Let's pull back even farther from the planet's surface. Against the blackness of space, Jupiter is surrounded by something unexpected, a faint set of rings encircling the gas giant. Shimmering like strands of spider silk, Jupiter's rings are nothing like Saturn's bright, sweeping arcs. These are thin, almost transparent bands of dust, so tenuous they weren't discovered until 1979. In this image, we see the main ring as a slender, bright line wrapping around the planet's equator, a dim halo within it, and a wide, diffuse gossamer ring extending outward. These rings sparkle in sunlight, appearing as a faint white line crossing Jupiter's night side. They are 1,000,000 times fainter than the planet itself and are composed of tiny dust grains, not brilliant chunks of ice. So what maintains such structures around a colossal planet? The answer lies right in orbit, Jupiter's small inner moons. Two of these, Amalthea and Adrastea, appear as faint points of light within or near the rings. In this image, Amalthea is visible on the left edge of the ring system, a tiny white dot with a barely noticeable diffraction spike, confirming its presence in JWST's infrared view. The even smaller Adrastea appears as a speck of light on the very edge of Jupiter's main ring. These rings exist because the moons are constantly replenishing them. Unlike Saturn's icy rings, which may be remnants of a shattered moon, Jupiter's rings are formed from dust created by micrometeoroid impacts. When space debris strikes the surface of tiny moons like Adrastea or Metis, it kicks up particles that drift into orbit around the planet. And over time, countless impacts form a dust ring. Adrastea, only about 12 miles across, orbits right at the edge of the main ring and is its primary material source. The slightly larger Metis, though not shown here, contributes as well. Farther out, the moons Amalthea, about 155 miles wide, and Thebe emit dust that forms the faint outer braids of the ring. Data from the Galileo spacecraft confirm this mechanism. Jupiter's rings are indeed composed of dust blown off its small moons. The vertical thickness of the main ring is just a few miles. Up close, the particles are microscopic bits of silicate rock, likely dark in color, which is why they reflect so little sunlight. They're virtually invisible unless seen in infrared or angled and with backlighting as we're doing now. There it is, Jupiter, a dynamic system in its own right. Atmosphere, magnetosphere, rings, and moons, all bound in a complex gravitational and electromagnetic embrace. We observe atmospheric bands stretching across its latitudes, holding storms and channeling energy from within. We feel its internal heat still radiating from a primordial furnace, fueling convection that gives rise to thunderstorms and towering clouds. Invisible lines of magnetic force reach from its depths, linking to the auroras at the poles and coursing through Io, driving electric currents that make the polar skies glow. Jupiter's rotation ties all these elements together. Its rapid spin shapes the bands, aligns the cyclones, shifts the magnetic field, and even helps maintain the rings in a flattened disk. From this perspective, the planet is a symphony of motion and forces. Fluid dynamics, electricity, magnetism, gravity, all playing out on a grand scale. Now all these elements come together in a single portrait. Jupiter is a world of eternal change and immense power. There's no need for a conclusion because, whatever we say, Jupiter remains what it has always been, a majestic, mysterious, and forever dynamic gas giant, holding with it echoes of creation and the ongoing drama of the cosmos.